Well, hey everybody. This is Obi-Wan Pez for N-Simplex Pachinko. This has got some real French vibes to it. Could be doing some math tonight. Don't know how long I'm gonna be on, but you know, something anyway. If anyone has any questions about math, feel free and drop that in chat. And we'll see how long we're gonna be on tonight. Probably at least an hour, probably 90 minutes. We'll see how it goes. I do have to wake up slightly early tomorrow, but it's fine. Oh, and my aspect ratio is back to normal, so that's good. Yay. I think it was being downscaled to 720, but apparently that was an inappropriate aspect ratio or something. I don't know. Whatever happened. And I turned our bitrate up to 4000, so we'll see if that holds and doesn't cause any issues. Yeah, whatever settings were recommended on some random website, I was like, okay, let's just do it. So yeah, hopefully it works out okay. Righto. So anyway, in the meantime, yeah, sure. Can take a look at Differential Equations by Phillips, 3rd edition. And the guy who owned it before wrote quite a few headings, like section headings in there. It's kind of interesting. I think he was teaching out of this book. 3rd edition, 10th printing, H.B. Phillips, Ph.D., head of the mathematics department at Massachusetts Institute of Technology. Copyright 1922, 1925 for the 2nd edition, and 1934 for the 3rd edition. 10th printing, September 1946. So it's quite a while in between. Chapter 1 has to do with the differential equations of first order with variables separable, so separable differential equations. Chapter 2 is other equations of the first order, so we have exact differential equations, those that require integration factors, linear differential equations as a general general process, equations that are reducible to linear form, homogeneous equations, equations that are reducible to homogeneous, equations of higher degrees, geometrical representations, change of variable, and simultaneous equations. So simultaneous equations, this actually agrees with what I was talking about earlier, that this is essentially systems of first order linear differential equations, and putting that stuff kind of towards the beginning of the course rather than at the very, very end of the course like I had taught the first couple of times that I did differential equations. So it's interesting. Alright, then in Chapter 3 they move on to special types of second-order differential equations. So the general theory, equations that are not immediately integrable, equations not containing y, so those that just are on y prime and x, so y prime as a function of x, essentially. Equations not containing x, those are called autonomous equations. So those are, generally speaking, equations that are y prime is equal to f of y. Linear equations of the second order. And this is where we get into the fun stuff. So anybody who's taken differential equations before, this is where we end up doing our characteristic equations and trying to solve for eigenvalues, eigenvectors, and getting the general solutions. They go into homogeneous equations, deflection of beams, equilibrium of a cable, motion of particles in a straight line, motion in a plane, motion of complex systems, motions with systems with variable mass. Variable mass, interesting. Chapter 4 goes into linear equations of constant coefficients, so equations of nth order, linear equations with constant coefficients, equation with right-hand member 0, so that is homogeneous equations as we know them. I don't know if this is using any different terminology. It shouldn't be. Right-hand member function of x, so non-homogeneous. Those that have imaginary roots, so we've dealt with this. This is like harmonic systems. And then in chapter 4, this is where we get our symbolic methods, method of undetermined coefficients, variation of parameters, homogeneous linear equations, simultaneous linear equations. So touch on that a little bit more. I gotta figure out then what simultaneous equations in chapter 2 is all about, because that might be different. Rotation about a fixed axis and vibrating systems. So fun, cool stuff. Cool. So, Phillips starts with same basic stuff that we do in modern differential equations. Start looking at the definitions of, for instance, what is a differential equation in the first place. So here we're saying that we've got something that looks like x squared plus y squared dx plus 2xy dy is equal to 0. Or something like second derivative of y with respect to x twice times x minus first derivative of y with respect to x is equal to 2. They are differential equations because they contain differentials. So here we have our differential portions. And yeah, sure, they mean something slightly different in multiple contexts, but overall, right, they mean the same thing. We're taking a derivative of a particular variable with respect to a particular variable, or we're leaving it in general form up top. So this is our like true differential form. So oftentimes I'll call this general form, or like general as in it's non-specific. That isn't exactly what it means to other people, so do check your definitions with your particular instructor. It might be different. And again, if anybody's in and wants to drop a question in chat, feel free to do so. Alright, these are all ordinary because they have ordinary derivatives. And then truly, like, what does that mean? Well, we're looking at this in terms of having derivatives which are talking about, like, trying to find what is the change in this particular measurement, whatever y is, with respect to x, our independent variable. And there's only going to be one independent variable, generally speaking, if you're talking about ordinary derivatives. And then when you get into the more complicated stuff, there is also partial. And in partial derivatives, what you're doing is you're trying to show that a particular movement in, let's say, our x direction only is going to cause some change in our temperature, for example, or some change in, you know, whatever particular value it is that we're trying to measure. So our independent variable, our independent variable can have multiple independent variables, and so that makes it a little bit harder to work with sometimes. Most of the time, let's be honest. But generally speaking, it's going to look something like this. Second derivative with respect to z. Nope, sorry. Second derivative of z with respect to x both times, plus second derivative of z with respect to x, nope, y both times is equal to 0. I don't remember which one this is. I think it might be the heat equation. No. No. It's the second derivative. The sum of the second derivatives is equal to 0. Some of its second partial derivatives, yeah. Pretty sure I got rid of the book that actually I definitely know had it in the beginning, because the rest of the book was kind of crap. Let me see. Second derivative, or partial derivatives, you say? Elements of partial differential equations by Ian N. Snedden. So this does have multiple chapters that are on, like, particular formulations of various derivatives. I think this might be in the order in which it is solvable, based on the methods that are being discussed. Which, like, yeah, it's fine. Guess who doesn't do that? Cauchy problems? Nope. Hey, there we go. Partial derivatives of the second order. Given two functions f and g, show that this is true. Blarg. So it's the second gradient. Second gradient of any particular function. Ah. Nope. Almost. It's Laplace's equation, essentially, or the harmonic equation. The second derivative of a particular function, the gradient of a particular, second gradient of a particular function is equal to 0. Alright, see, I knew it had a name to it, like somebody in particular. So it's often called the Laplacian operator, or del squared. Granted, right, squared isn't really second derivative, but whatever, it's fine. My son was up late tonight. I think he was feeling guilty about something he did. Or maybe he was actually just couldn't sleep. But yeah, he decided to create a essentially Macy's Day float. Is a snake. He's a funny kid. So back to here. Okay. Alright, so the Laplace equation. Is one of the partial differential equations. And in both of these cases, we also have an order. Because we have taken a single derivative of this particular function. Well, it's not a function necessarily, but we've taken a single derivative of the equation that was here and separated it into dx and dy pieces. On the other hand, these two here are of the second order. Alright, so those are of the second order because we've taken two derivatives in each of those equations to something, right? So we look at whatever the highest ordered derivative is going to be anywhere in the entire equation. So in this case, up top it's 2, and then at the bottom it's also 2, although this one is a partial derivative, the other one up top is or in the middle, is an ordinary derivative. Same deal. So classification becomes important as we go on through the course, due to the fact that eventually we're going to say, like, well, problems of this kind or of this particular classification are solvable by the following methods. We'll have like a, group of tactics that we can use against it to see what'll work. Okay, so the third and the first, somewhat interestingly here, both have right-hand sides of their particular equations as 0. Now, it doesn't have to be the right-hand side, but usually it's isolated over on the other side, and usually it just has no derivative terms on the other side. So, you know what, we might as well just get rid of that. That's fine. So the thing that has no derivative terms, or the equation that has no derivative terms, is said to be homogeneous. And the fact that this is not 0 means that this one is going to be non-homogeneous, or sometimes inhomogeneous. And there was a new one that somebody said the other day that I can't remember what it is now, which is really too bad. I'm wishing I remembered what the classification word was for that one, but right, this has a when it is 0, then it's homogeneous, and when it is not 0, that's when it gets the name non-homogeneous or inhomogeneous. So either of those work. Again, like I said, I think I heard a new one, or at least, you know, a new one to me, where like that particular property, our derivative, our thing with no derivative terms, is itself a function that is or is not 0. That'll get its that'll get its homogeneity status. Okay. Just go like that. And the other one that we have is the linearity. Oh. So the linearity is a little more difficult to describe, but the idea here is that we end up with the terms are all going to be linear in the dependent variable and its derivatives. So in the previous examples here, our top one is going to be nonlinear. Technically, if we assume that y is going to be the dependent variable and x is going to be the independent variable, or if we go the other way around, it doesn't actually matter. What we're going to find out is that If we make it either dx dy or dy dx in the associated locations, then what's going to happen is we're going to have multiplied onto that term, our dx dy or dy dx, we're going to have in the dx dy term, we've got an x squared that's being multiplied to it. So it's not linear in x. And if we go on the other side, then we've got 2xy dy dx, and that is not linear in y. So no matter which one is independent or dependent, it doesn't matter. That top one is actually going to be nonlinear. It doesn't necessarily have to be difficult, but I will say that most nonlinear differential equations in general are going to be more difficult to solve. So 1, right, from before. 1 is going to be nonlinear. Whether it was in x or y, again, it doesn't matter. This is x squared plus y squared times dx plus 2xy dy is equal to 0. Again, didn't matter which variable we take as dependent or independent. Either way we go, we end up with a nonlinear differential equation. So, becomes, again, more difficult unless there's a specific set of circumstances. Alright, in our second one, we have pretty clearly y is going to be our dependent variable, x is going to be our independent variable, and in here we have a function of x, which is being multiplied onto our second derivative of y. That is linear in y, or in this case, in the second derivative of y. Alright, next term, we've got a minus 1 times dy dx. That is linear in y prime, or linear in dy dx. And then the other side doesn't have a y at all, so we just don't consider it. Now, I will say that this would also be linear in y. If x was a much more complicated function, it would not matter at all in the least. If I went, okay, this is f of x times second derivative of y over second derivative, or with respect to second derivative of x, wouldn't matter one bit. No matter what this function is, as long as it only has x as its independent variable, and there is no y inside of it, then this term is still linear in y, or in this case, linear in the second derivative of y. Some people get a little bit confused about that, but again, linear just refers to linear within that particular variable. And our third one, the partial differential equations. Again, this is going to be linear in second derivative of z with respect to the second derivative of x, or with respect to x twice and with respect to y twice. There's nothing attached to them except constants. So, yeah, they're linear. If you just got here, welcome on in. My name is Obi-Wan Pez. This is in Simplex Pachinko, and we are talking about differential equations. If you would like to ask a question, feel free to drop that in chat, and I will get to you as soon as I can. I will attempt to prattle on as little as possible. And if you are a member of the Math Twitch community, you feel free to heckle. It's fine. Not that you need permission. Okay, so that means that overall, number 1, which was this one up here. On the real, how's it going? We're using Excalidraw, which was not my first choice, but it works all right. I found that Microsoft Whiteboard was pretty good. It had its quirks, it had its problems, but it was what I got used to, and it had the functionalities that I wanted. Excalidraw doesn't let me um, like go back to anything that I had before. Now it may just be that I need to do Excalidraw Pro, and it'll have a memory. But I'm not super willing to pay for it, so unless it's really like primo. Yep. But you know, for somebody who might be like doing a tutoring session, doing Twitch, doing whatever, and not needing it to like back up all of its actual pictures, yeah, it works. Or YouTube videos for that matter. Okay, so this was at the top, number 1. Let's actually label them maybe. Novel idea. What's 1? All right, so number 1, we said that this was a first order, ordinary, homogeneous, nonlinear differential equation. So to get that in the, you know, proper order or whatever, you'd have to look up which adjectives actually belong in which order, but whatever, it's fine. Generally speaking, our categorization starts as ordinary or partial. Order. Is it linearity or homogeneity? I think usually we do linear. Yeah, usually I think we do linearity immediately after order. Sorry, this is nonlinear. And homogeneous. Differential equation. In case anybody is confused about what we're talking about. So, our second one was also ordinary. This was ordinary. It was first order. Nope, this is second order. Right, we talked about. This has a second order derivative, so it is a second order differential equation. And then this was linear and non-homogeneous. So, ordinary, second order, linear, non-homogeneous, differential equation. And third, we had a partial, second order, linear, homogeneous. Differential equation. So anyway, that's what we got there. If anybody has any questions on that, again, let me know. We'll try to... Oh, let's try and bump this up just a little bit. slightly. Yeah, it'll work. Hopefully it won't bother people too much that it's slightly off-center. That's fine. Hang on. Let's see. Can we get this? Yeah, that'll work. Okay. Right. There we go. So with classification, we've got all these different ways to classify differential equations, which can help us start to understand, like, okay, well, if they have a classification, then they're going to have some sort of like grouping system, which might end up helping us solve things. So to solve differential equations in general, we've got a whole bunch of different methods that we can try to use. The easiest one of them all is going to be separability. So generally speaking, separable differential equations are going to be a little bit like the first one that we had on the previous section. That one actually doesn't technically work the way that the way that we had written it, just because it mixes our x's and y's. But separable differential equations are going to be things like, you know, x dx minus 2 y squared dy equals 0. So in this particular case, we have a differential equation where all of its individual terms are separated by the variable that they have. So our first stuff over here has all of our x's, our second stuff here has all the y's, and there's nothing else. So that's it. In general, right, this is going to, let's solve this one first. So personally, I like to split them on either side. It doesn't really matter which way you do this, but if we want to make this x dx is equal to positive 2y squared dy, now what we can do is take the antiderivative of both sides, and we could see, hey, this already had a dx and a dy attached on either side, so we could just look at it and say, okay, well, if I take the integral of, or antiderivative of, x dx, what do I get? Well, this is a power rule, so this is going to be a half x squared plus c, and yeah, okay, we'll do that. All right, and then here on the right, we have the antiderivative of 2 y squared dy. The 2 can come out because we don't really care about it for the moment. And then here we're saying, oh, that's another power rule. It's going to be y to the third. We're going to increase the power, but that will exchange with dividing by or multiplying by the reciprocal of the new exponent, which is 3. So that's going to get us a 1/3 out front. And then we had the 2 that was there originally, so we could just multiply it in, make it 2/3. Makes it nice and easy. And then we say plus c. But that's a slight problem, because this doesn't necessarily have to be the same constant as the other one over there. So we just label it c1. And if we're typically trying to solve this for x, we could say, okay, well, everything needs to be over on the other side. So let's shift everything not y to the left-hand side, which means that we get like c minus c1 plus a 1/2 x squared, and then we're going to eventually deal with the coefficients there. So 2/3 y cubed, and this here is just a constant, so like whatever. It doesn't matter. We could just label it. All right, let's just c. Okay, and then we can also take our 2/3 that we had here and say that we're going to multiply this by 3/2 because we're just trying to combine everything. This ends up getting us a 3/4 as the coefficient up front. And you know what, let's just, I already wrote it, let's just do the 3/2 again here, and we'll deal with it on the next one. So y cubed is going to be equal to 3/4 x squared plus, this is going to be 3/2 of the previous constant, which is just another constant. So if you want to just label that as c as well, yeah, that's fine. Right, we're just carrying this through. It doesn't have to be labeled something different. So you just leave it as is. It's good. Some arbitrary constant, we call it c. No matter what we do to it, as long as we manipulate it only with constants, we can just leave it as a constant. Okay, and if we want to, a cube is a one-to-one function. So let's take the cube root. This is also a one-to-one function. So we don't have to consider any like weird stuff going on, skipping powers and things like that, as would happen if you had an even exponent on y. So here this is just going to be y is equal to the cube root of 3/4 x squared plus c. Phobos! Yep, you got it. Welcome on in, anybody who is new. My name is Obi-Wan Pez, and this is The Simplex. N Simplex Pachinko is our channel name. So, we like to hang out whenever we can and do some math. We had a request. I was on somebody else's channel last night, and they were like, nobody's on, like, tomorrow. And I was like, well, I'm going to have to change that, I guess. So, that was the reason why I did this today, specifically. So, let's see. Yes, that was Dawn. So, let me... Let me shout out everybody. These are the Math Chads. So we have Dawn. Dawn does math. We have Zach at e to the 2i pi. Penn Center. E.N. Stuckey. Obi, that's me. Danny Highway. And Dr. Gold at Actual Education. We are kind of the core group of, like, not the only core group, but the core group of math streamers who got together over this past winter. We were like, hey, we also do math. Let's be friends. So we've created this nice little professional / friend community of like-minded math streamers who all get together and kind of hang out, throw some math each other's way, and throw raids each other's way, and occasionally play some games. Speaking of which, we will be playing Good Job at some point soon. Good Job is a Switch game in which you are playing a nepotistically hired young 20-something who is the son of the CEO, or, well, child of the CEO, but given the antics, I'm slightly inclined to believe son of a CEO. The cutscene at the beginning ends with your father kind of waving from the top and calling you up, but that means that you have to like work your way up the corporate ladder, if you will. We have a particular scorecard, which is based on the time in which you complete the level, the number of objects that you have collected. There's collectibles that you can get, so the number of collectibles that you spend time collecting. In the run in which you have the best time, which it doesn't necessarily have to be the best time, but most of the time it is, how many objects have you broken, and what was their total worth? So there is some objective function which is sort of hidden to me, which takes those 4 factors, compresses them into a score, and you get a score on each of the rooms that you complete. And we're trying to get up to 8th floor, I think, in order to, I'm going to guess, have our lunch break with Dad or something like that. And if I'm honest, it doesn't have to be Dad, it can be Mom too, or whoever. So, just again, based on the antics, the laws of probability, I think we got a pretty good guess here. This is a father and son. But feel free to self-insert if you have played this game, because, oh, wow. On floor 2, they introduced the forklift. There was much destruction that day. Okay, so separable differential equations look something like this. In general, right, we can generalize separable differential equations to look like some function f of x times dx plus some function g of y dy is equal to 0. Right, you will be able to, in a separable differential equation, you will be able to simplify your equation into this form. And most of the time, generally speaking, right, we're going to find whatever functions we have here. This is going to be our, like, f of x dx. It's going to be equal to a negative g of y dy, which, again, could be generalized as just g of y dy. It doesn't matter. Move it to the other side, and then take the antiderivative of both sides. Antiderivative of f of x is capital f of x plus c is equal to, you know, negative capital G of y. Again, our c's will combine in some way, shape, or form. You get something that looks like this, and then again, it's going to end up as a, according to our original notation, not necessarily the only notation that exists. Again, our c here is an arbitrary constant, so negating it, there we go. Negating it doesn't actually change its, you know, arbitrary constantness. So we have here that negative capital F of x plus c is going to be equal to capital G of y. And if g is 1 to 1, then our y is going to be equal to big G inverse of negative f of x plus c. So, like, we can really solve this generally if g is a one-to-one function. If not, yeah, it's not that huge of a deal. It's fine. Now, I've got, I'm going to be very happy when I get my desk back and my desk chair. Because right now we're still sitting on the floor. It's fairly uncomfortable, but, you know, what can you do? It wouldn't be so bad if I had my, I've got a chair, and I think it's like a camp chair or something, or like a hiking chair. It sits on the floor, you've got about yay much padding, so, you know, like an inch of padding, and it goes, you sit on it like that, and then it has, the like snap clips here and here, so that you can actually lean back into it, and it just rests here naturally because of the way you're balanced and the tension that's on the webbing. Kind of wish I had one of those again. I don't know where it went now that I'm thinking about it. I wonder if it broke somewhere along the line. It could also be sitting in storage. That's unlikely. Nah, I would have seen it. So it must have broken or it got lost somewhere along the way. But yeah, so we had a bunch of camping equipment in Maryland that we were not able to bring to the UK because it very well could be contaminated with, you know, microbes and all sorts of other unpleasant stuff, or, you know, lantern fly or anything else like that. And we don't need some sort of touche. And we don't need any to bring in any sort of invasive species, be it plant, fungus, or animal. Yeah, Yorkshire is very nice. I don't want to ruin it, so they were like, it was going to have to sit in storage for potentially up to a year, and we're like, by that time we're starting to think about heading back, like. We'll just borrow camping equipment from the people who live here, you know, or up the street, or on base, or whatever. Because I think the military base has camping equipment that you can borrow. So, okay. So we have here, generally speaking, right, separable differential equations can be solved by separating those things and then doing the thing. Yes, covered in local fungus. I'll take my chances with the local fungus. Right, our bodies can fight it just fine. Okay, so the hell? That's a mixed differential equation. That's not separable. Yeah, alright, that one works. So, more fun, slightly, for some definition of fun, is going to be something like x dy plus 5 minus y, 5 minus x, nope, 5 minus y, wow, dx equals 0. So if we go this way, now you notice that, well, hang on, this is not separated because our x's and y's are now mixed. Okay, fine, but good news, this is separable. So in this particular case, we're going to get dy times our x, and then we can set this equal to, subtract 5 minus y from both sides times dx, and we end up with y minus 5 dx. Okay, and now we can probably see, oh yeah, this is a separable differential equation because we can divide both of these terms off from the side that doesn't have its variable to the side that does have its variable. So here, again, we divide all this stuff by x. We divide all this stuff by y minus 5. Right, and the left-hand side ends up becoming dy over y minus 5 is equal to dx over x. We can see here, now it is separated. Cool. So we say, okay, we're going to take the antiderivative of both sides. Over on the left, this is the natural log of y minus 5. And over on the right, this ends up becoming the natural log of x. Okay, and as always, we want to try to solve this for y as long as there's not any issues, especially concerning non-one-to-one functions. In this particular case, right, natural log is 1-to-1, so we're okay with that. We can exponentiate e to both sides. So again, exponentials are also 1-to-1 functions. And e to a natural log of something is just going to be that internal stuff. Yes, yes, plus c. It actually does matter this time, right? Because natural log of x plus c, thank you. Okay, it does matter this time because here what's going to happen is the left-hand side, in the way that we did it, and it doesn't actually matter if you put the c on either side, because again, same thing will happen eventually. We end up with just y minus 5 on the left, and on the right, okay, we have to separate it first, but whatever, it's fine. What happens is we get two exponents which are being added, therefore we can split this into two different e to the natural log of x, which is just x, times e to the c. And what is e to the c if not just some c? Right? It doesn't matter, it's just a constant, so it's fine. So we end up with y is equal to, this is cx plus 5. And if you want it to be mx plus 5, we can also do that. People might get a little into their default linear equations. Don't want random c values to be the slope. How dare. Okay. something. Ah. So there's a slightly different method that he highlights in this book, which is equivalent, so it's not like it really matters that much. But if we went with like x dy plus 5dx minus y dx is equal to 0, or if these were like separated by a bit, maybe you don't see it like the whole way, you're kind of like, I don't know what exactly is going to happen. Oh, no. Let's not do that. Trying to think how I might salvage it. This is probably not going to be better. No, this is not better, so never mind. Sensation! We demand popularity. Yes, so when you solve the last one, you divide it by x. So let's back up there. Right. So in here, right, if x were 0, then we get, see, that, let's just throw stuff around, it's fine. If x were 0, that would mean that we get 0 dy plus. Now we have an equation which actually has to be solved a specific way. So this would be 5 minus y times dx is going to be equal to 0. Yeah, never mind, because dx is going to be 0 as well. Okay. I got you. Yeah. So y is arbitrary. If x is 0, we're going to get what's called a trivial solution. So that is actually an important point. Thank you. So in many cases, and this is also a y invariant. So if it were given to you in a different form, like dy dx is equal to y minus 5 over x, then we would actually have a different kind of equation that we'd be working with. Right, it's very close. It's related, but in this particular case, we can say, okay, if x is equal to 0, then what we get here is that dy dx is undefined. And what that means for us is that the slopes of tangent lines are that's not even slopes of tangent. Okay, the slopes of the tangent lines are okay, undefined. It's fine, right? Which then also means that the tangent lines themselves are vertical along x equals 0. Well, x equals 0 is vertical. So all that means is that we're going to now have a location where if we get a solution, or if we have an initial value which is on that particular line, the only solution we're going to get is a vertical line whose equation is x equals 0. So what we would look at, another way to do this is to create what's called a slope field. That's just beautiful right there. Create a slope field that says, okay, what would the tangent lines look like at any particular location? So we know right now our tangent lines along x equals 0 are going to be vertical themselves. That should be vertical. When you're doing these sorts of things, you eyeball it a lot, so it's not like it particularly matters that it's not straight, but we could always just use the actual line tool and create a straight line. It's fine. Assuming that this is also how you would do your homework in an actual class, right? That you'd be hand drawing all this stuff probably, or at least I would encourage it. There is actually some research done. There has been some research done that has shown that students who are working with pen and paper, doing things by hand, actually remember stuff better on average than people who are working in computers. Now, the people who do both, generally speaking, have more options in order to be able to remember things. So there could be a little bit of bias in that particular direction. There also could be bias away from the computer crowd just because of some hardwired stuff, because we've had, roughly speaking, 6,000 years worth of writing that we've been doing. And it is a tactile sensation to take the stylus of a pen and make your cuneiform tablet, right? That sort of motion makes that internal connection to your mind. Like, I am now connected to this piece of clay. And in our society, we don't use cuneiform anymore, but still, we make these sweeping motions with our pens and pencils, totally pencils. And through making those sweeping motions, it actually affects our brains in sort of an interesting way. And some of that could contribute to actual better memory. I think that's just really cool. Is it 100% guaranteed? No, absolutely not. All right, that's just some suggestion as to what the research says. Might not be true at all. We'll have to see. Some other pieces that we're going to look at here, some other stuff we like is, for instance, when does dy dx equal 0? Right? That is when the numerator is equal to 0, so y equals 5, or y minus 5 equals 0. So this is saying that we have horizontal tangents along y equals 5. Stroke orders of characters in Chinese. Yeah, I imagine. Oh, man. Okay, so now we say that when we have y equals 5, let's call this y equals 5. We're going to have horizontal tangent lines. Now there is one thing that some of you should be screaming about right now. See if you figure it out. Okay? And then if we're going to do this, we're also going to say, all right, let's figure out some other like relationships that exist here. We've got y minus 5 over x. Okay? Where are the slopes going to be equal to 1? Because those are nice and easy to draw. Right? So you could set it equal to 1, multiply to both sides. You get 1x is equal to y minus 5, add 5 to both sides. This is 1x plus 5 equals y. So y equals x plus 5. Along that line, which has a slope of 1, we get a slope of 1. Right, so along the line y equals x plus 5, we have a slope of 1. And when you're doing this stuff out, you don't necessarily like have to write this, but it is kind of good to help you remember how all this works, how it's all connected. Yes, exactly. 0, 5 is like, whoa, hang on, wait a second. You just said that the slopes are undefined along x equals 0, but now there's horizontal tangents along y equals 5. So, like, what happens at the intersection point of those things? And the answer is, we have no idea. They're undefined, but not in the same sense as the dy dx is undefined, so therefore it's vertical. So in this particular case, we can't say anything about what's happening at 0, 5. We just say, well, we don't know. So here, we usually put an open circle to say, we don't know. But yeah, it is super sketchy. Can't use that. Okay. Now, using the intermediate value theorem, we could say, okay, we've got a slope of 1 here. We have a slope of 0 here. So somewhere in between, we should have slopes that are in between. So any slope that I want to pick, which is in between 0 and 1, is going to be represented somewhere in there. And you just kind of have to think about it a little bit and say, like, okay, what's happening as we go out further from that particular, we'll call it a critical point, we can call it a null point. There's all sorts of stuff. Okay, I also should make that point a little more clear. So at this particular point, when we have dy dx at 0, 5, we end up getting 0 over 0. So not only is it undefined, but this is indeterminate. So if you remember from your, L'Hopital's rules stuff, right? That's messed up, man. We can't do that. And we can't actually use, like, L'Hopital's rule in order to solve this, because, again, what's going to win here? As we're approaching the horizontal stuff, we're going to get shallower and shallower slopes, and as we approach the vertical, we're going to get more vertical and more vertical slopes. So, like, there's not one value that you can approach. It's just going to be really weird. It's going to be different from, like, all different sides. Okay, so the major point here is that as we move away from our critical point here, what we're going to see is that as we move further and further left, we're getting further away from our steep slopes, which are defined by our x equals 0, and we can see here, this is where our slope is equal to 1, y equals x plus 5. So if we just keep moving further and further left away from this line, our slopes are going to become more, like it's going to have more of a component of 0 than it does of 1 or something very steep. So as we move far to the left, all of these slopes here are going to eventually become more shallow. So when we're just doing this like for homework and stuff, it's not typically like, oh no, we have to figure out what all these values are now. You just say, okay, look, as we move further to the left, our slopes of 1 become less slope of 1, and they're going to keep shallowing out as we keep going further and further over. So again, here we get something like that. Here's like that. Oops. Wasn't good enough. It's like that. It's like that. They'll never actually become horizontal. Okay, and likewise, right, all of these here end up becoming stuff like this. Okay, all the stuff down in this octant, I guess, is all going to become, as we move toward x equals 0, it becomes steeper and steeper and steeper. So stuff immediately under it is going to have a slope of just over 1. But then as we get closer and closer to x equals 0, it becomes more and more vertical. Nope, that's shallow. I need steeper. And again, not quite vertical, but like, you know, it's getting there. And they should be always steeper as we're moving to the right toward x equals 0. Okay, and on the opposite side, we see the same thing happening. So here we're going to get, this is also going to end up being, I should probably be a little more clear about what's happening here, right? As you move over to the right-hand side into this lower right section, and I meant octant and now quadrant in terms of like our axes that we've created here artificially at x equals 0 and y equals 5. So this is like the central point, and then coming out from that, we're going to have these different values. Okay, what do we have? Well, this is all y values that are less than 5. So our y value here is less than 5. Means that minus 5 is going to be a negative value, right? Y minus 5 is negative down here. And our x values at the bottom are all going to be positive. So every slope in this region is going to be negative. And again, it starts out being very negative, really close to x equals 0. And then as it gets further and further to the right, it's going to shallow out and eventually go towards 0. Now I suspect if we also want to know where dy dx is equal to -1, we're going to get negative x plus 5 as our equation. And then we can always just prove it, right? So dy dx is equal to -1 is going to multiply our x to both sides. That's going to get us a -x is equal to y minus 5. Add 5 to both sides. It's -x plus 5. Ta-da! So y equals -x plus 5. All right. If anyone has any questions about mathematics, feel free to drop it in chat. You know, it's what we're here for. So this is just me going on a tangent about differential equations, which is generally speaking my specialty. Okay, and then likewise on the other side, over here, these are going to be magnitude less than 1, get shallower and shallower as they go out. Something like that. And likewise in the top quadrants or octants, we can also do the same thing. So we can look at it in terms of, okay, these are going to be slope, again, very close to 0, and increasing. Oh, sorry, they're still going to be decreasing as we go further out. And then over here, these are going to be much steeper. Oops. Okay. Now what does this mean? Well, if we were to select any particular starting point, say here, what we would get here is a particular solution that ends up, and I should have realized this faster. Yeah. Jazzy. What we're going to get here is a solution that starts at our neglected point here, 0, 5, and then goes out as a ray. Exactly 100% away. Right, the solutions were linear. I should have looked at that when I was doing this slope field. Right, if I pick another point, let's say here, this is going to follow, this particular set of tangent lines that are going out in this particular direction. So I can pick any particular thing I want, and then I can show that these get us different solutions that are just all over the place. It is also possible, potentially, that the solution would include the stuff on the other side as well. So I don't know 100% if, like, this one would also include that. This one would also include that. It does give you the equation, y equals c times x plus 5, where c is defined by the point that you were given. And the only thing that you would have to note is that 0, 5 is not a point that is allowed to be part of that function. So there was something that we lost along the way, which was that the original equation had a problem point at 0, 5. You know what? The original equation did not actually have a problem point at 0, 5. It was our formulation that we made had a problem. So, like, our original function, our original differential equation was this thing here. Right? X dy plus 5 minus y dx is equal to 0. If you plug in 0, 5 as your point, then it's fine. Right? And if you let y be equal to cx plus 5, then it just ends up coming out as a very nice as a very nice true statement. So remembering the context in which our question was asked is going to be important. Because again, it doesn't actually matter that... I'm going to get rid of this thing because this was just ridiculous. So this was x times, so y was equal to cx plus 5 dy is therefore equal to c. So this is x times c, which was dy, plus 5 minus y is cx plus 5 dx is equal to 0. Here we get cx plus dx should probably just be 1. Yeah, wait. Never mind. We're good. When you take the derivative of a single variable and get a single variable back, then again, this is going to be... we took the general derivative operator of both sides. Right, so we go over here, we go, this is the derivative of y is equal to the derivative of cx plus 5. That gets us that. So this is cx dx. Don't get cute. And then over here we've got 5 minus cx minus 5 dx is equal to 0. And again, cx dx. This is a plus 5 and a minus 5. That's 0. And a minus cx dx. Cool. So same thing, minus or thing minus itself is equal to 0. True statement. So it doesn't even matter what C is, what slope we started with. We're always going to end up getting something that works here. This is a good way to check your solutions to make sure it actually does come out to be something reasonable. Okay, I'm going to stretch because my back is getting sore already. So if y'all would, hang around, check out the other math chads as well. Again, we have Dawn Does Math, Zach at e to the 2i pi, Penn Center, En Stuckey, I am Obi-Wan Pez, and this is N Simplex Pachinko, Danny Highway, and Dr. Gold at Actual Education are the core group of streamers who have gotten together and said, yes, we want to kind of loosely team up and be kind of friends with each other and Twitch colleagues. We have not done anything, technically official. We don't have a Twitch stream team or anything like that. But, we just like hanging out in each other's streams and occasionally heckling from the sidelines. That's fine. All right, get up and stretch. Refill your waters. Cycle it in and out if you need to, and I'll see you in 3 minutes. Be right back. Righto. Welcome back, everybody. All Alright, let's jump ahead to the exercises section here. And for those of you who are interested in separable differential equations, feel free to try this out at home. Those of you who have no idea what I'm talking about, don't worry. If you've done Calc 1, you could probably follow along. If you haven't, welcome in anyway. And if you have any questions, feel free to drop them in chat. I will get to them as soon as I can. And by problems, I do mean, like, you know, anything, including Algebra 1. Including pre-algebra. If you want to, you can include anything about education or mathematics education in general. So I have been teaching as a two-year college professor. I made it to the rank of associate professor, which would require me to do something like a 3-year-long project and an overhaul of a course, and then do the statistics and a write-up, thereby granting me full professorship at my 2-year university or 2-year college. I was not particularly inclined to do that over the last few years, and that's a lie. It's only been like a year since I got my promotion. So I was not inclined to start on it immediately, and so I have attained and remained an associate professor up until this January, when I quit because we were moving to the UK. Everybody at the college knew about it. You know, basically when we decided end of last year in May, maybe in August, when we were like, yes, this is finalized, we're doing it. I came back and was like, hey, just to let you know, I'm not going to be around much longer. Okay, so maybe we do one that's a little crazy over here. Numeric approximation of derivatives. Sure, give it a shot. So if you're talking like Calc 1, Calc 2, yeah, definitely. If you're talking about the like numerical analysis class, which is a senior/master's level, maybe. Let's do one that's a little weird. So we got tangent x, sine squared y, dx, plus cosine squared x, yes, times the cotangent of y dy is equal to 0. So, I guess, like, what context? Because there's... like, if you just have a function, y equals, I don't know, 12x to the 5th minus 7x squared minus 10 times the cosine of x. I don't know, something. You know what? Not 12. Let's do 2. Ease there, killer. And let's do 3 there. Right. Take it easy a little bit. So if you're trying to find the second derivative of this thing, your first derivative, again, power rule here, 10x to the fourth. I misjudged this a little, that's fine. Minus 14x 3. Derivative of cosine is positive sign. Sorry. Derivative of cosine is negative sign, which switches the sign in front. And second derivative, again, power rule. Cosine x. And then you want to evaluate this at some value, right? Like, what's y double prime at, like, 3? And you're going to be able to plug all this in and get those values. I imagine that's not what you're talking about, and it's probably harder than that. Is this like you have a bunch of data and you're trying to find its acceleration? Simulation of a differential equation. Okay. Do you have a set time step or dx that you're using? So, let's see. So, you have a differential equation, which is stated much like this, where it's just like, here's a series of functions, whatever it is. Doesn't matter how complicated or whatever, the computer can figure it out at least easily enough. Or you can derive anything. And if it's ugly, then you can get the computer to derive it. But taking derivatives is not a problem, right? If you started a differential equation, it has either... Okay. If you started with a differential equation, it's got either the first derivative that we can literally see in this equation if we, again, move it to dy dx. In this equation, we've got the second derivative and the first derivative. And then in this one, it's all second derivatives, and it's partial anyway. So, presumably, you can solve the differential equation for either the second derivative, which, if you're trying to find it, no problem, or you solve it for the first derivative and take its derivative again to get the second derivative. The other problem that might occur is that you've got a bunch of data that you're collecting, and it doesn't have like an equation that you know of, or it's a super complicated equation that you personally may not be able to like figure out what the individual second derivative is just because it's crazy. I mean, I've been playing Exponential Idle, wherein I've been trying to work out. Yeah, I've been trying to work out this equation. Try to find what is the second derivative. Boo. What is the second derivative? So what is rho double prime, rho double dot of this crazy thing with respect to each of the individual variables, which are going to be, you know, like, you have primes of them as well, some of which are given, some of which are going to be just numbers. Like, oh, if you plug it in right now, it's going to be, you know, 1 times 10 to the whatever. Yeah, sorry if I'm not understanding quite Phobos, but... I might have to see it in order to really understand. Alright, so this thing, we're going to treat it the same way as what we did with the other one. Everything that is a function of x needs to be over with the dx. Everything that is a function of y needs to be over with the dy. So we can divide all terms, and the right-hand side is 0, so that doesn't get affected. Divide all terms by the tangent of x. Nope. Okay, I think I ought to actually do this then. Divide all terms by the sine squared of y. Then also divide by the cosine squared of x. So on the left, we end up with tangent of x over cosine squared of x dx plus cotangent of y divided by sine squared y dy equals 0. I suspect this is going to be very nice and easy comparatively. This is a U substitution looks like. So if we actually manage to split cotangent, not cosine, take tangent, turn it into sine over cosine. So this is the sine of x over cosine to the third power of x dx. Plus cotangent of y is going to be cosine of y over sine cubed now of y dy is equal to 0. Right, so this is a U substitution in both cases. Individually, we can take their individual antiderivatives, and then if you really want to, you can do it on the other side too. Okay, so here we get if u let u be equal to cosine of x, then du is equal to negative sine of x dx. And this is going to be the negative antiderivative of du over u cubed. And if we let u be equal to sine of x over here, then du is going to be equal to cosine of x dx. Those are supposed to be y's. It's all cool. Okay, so then this is going to be a plus integral du over u cubed. Okay, with the notation that these are different u's. Okay, is equal to some constant c. That sounds an awful lot like a song from Schmigadoon. Alright, so here we're going to get a negative. This is, we're going to go up 1, so it's a negative 2 for our exponent. And we're going to divide by negative 2 as well. U squared at the bottom. Again, given that u is equal to cosine of x. Plus. Here we end up with a, this is the same integral, so 1 over negative 2 u star squared, where u star is equal to sine of y. Is equal to c. I don't necessarily recommend using u as technically both of your variables, but as long as you're remembering that these are local variables, not global variables, you can't use them everywhere, it doesn't matter what you use. So it's just for easing communication that usually I'd use like u and v as two separate things. Why I didn't just use u and v? Alright, with that, this is going to be a positive 1 over 2 cosine squared of x okay, minus 1 over 2 sine squared of y equal to c. And in most contexts, I would say that that is perfectly fine. Just leave it right there. Okay, it is in theory possible to solve for y, if you really want to. In this particular case, I would multiply all sides by both of our trig functions in order to get some terms where yeah, in order to get rid of the fractions. So if we really wanted to do it, you'd be hard-pressed to find anybody who's that interested in actually doing it. So if we multiply by 2 and our cosine squared and our sine squared, then we end up with sine squared of y minus cosine squared of x is equal to c times both. Okay, and then with that we're going to take both of our sine terms and move them together. So sine squared y minus c, so plus arbitrary constant on the other side. Sine squared y cosine squared y, alright, cosine squared x is equal to cosine squared x. Factor out sine squared of y. 1 plus c cosine squared x equals cosine squared x. Divide both sides by that cosine stuff. So sine squared of y is equal to cosine squared x divided by 1 plus c cosine squared x. And then at this point, it'd be like, we could take a square root, we could take the inverse sine, but overall, this is just going to be a mess. Right? This is alternate answer. You probably don't want to go any further than this. And if you really felt masochistic that day, you could say, okay, this is going to be sine of y is equal to, this is the absolute value of the sine of y, is equal to cosine squared x divided by 1 plus c cosine squared x square rooted. So therefore, sine of y is going to be equal to plus or minus the square root of this thing. And therefore y is equal to the inverse sine of plus or minus the square root cosine squared x divided by plus c cosine squared x. Again, I don't know why you'd want to. It is possible that this is going to get you, you know, functionally speaking, a better picture. But like, I probably would have left it way back up here with our sine squared is equal to, sine squared of y is equal to. And again, you could have left it all the way back up here. Alright, so let's try this out. Let's see what kind of answer we get. So this is going to be sine squared of y equals, this was fraction cosine squared of x over 1 plus c cosine squared of x. Add a slider for c, yes please. That's gonna be nice. C equals 1, we get this interlocking grid of cosines. If we increase c, they collapse, become smaller, shorter. Okay, and they're sort of like almost, they get to be almost like square waves. Okay, so then if we bring this down closer to 0, they interlock with each other. Nice. Okay, so before that they're interesting. Okay, so at this point they're almost straight in the middle, and then they very sharply turn at each of the edges. So if we make this go from -2 to 2. Right? So we have this at 2, whatever. And then as we start getting closer and closer and closer down toward 0, we get stuff that's almost like chain link, almost squares, but they're still curves. And then as soon as you move to 0, these are now actual squares. And it looks like there was some undefined value right at the intersection point. I can't tell. Alright, so then move down into the negative region, and oh, now it's horizontal. That's awesome. Or now the linkage is vertical instead of horizontal. That's really cool. I like that one. All right. Anybody have any other questions? Phobos, did you drop that into Penn's chat by any chance? If you want to, I can check it out there. Forward difference, nice. So I was only thinking like, I was thinking about methods which are for finding solutions to differential equations, but not so much for going the other way and trying to find what derivative values of the differential equations will be. Okay. That one's not hard. That one's ugly. I don't want to do that. Alright, let's try this. E to the y multiplied by dy dx plus 1 equals 1. So realistically, we want to multiply this out first. So this would be e to the y dy dx plus e to the y is equal to 1. Alright, then separate variables by multiplying by dx. So this is e to the y plus e to the dy plus e to the y dx is equal to dx. Okay, so now we want to combine the dx terms. So this is going to end up being e to the y dy is equal to parentheses 1 minus e to the y dx. And we can divide through by 1 minus e to the y. So this is e to the y over 1 minus e to the y dy is equal to dx. Okay, so if we let u be equal to 1 minus e to the y, then du is going to be equal to negative e to the y dy. Which we don't have because we need a negative then. So this is a negative integral of du over u. So it's a natural log. Is equal to, this is going to be x plus c. Negative integral du over u is a negative natural log of u equal to x plus c. Give the negative over. So natural log of u is equal to negative x plus c. Again, just an arbitrary constant, so if it gets negated, you can leave it just as c anyway. Doesn't matter. And then we need to exponentiate so that we end up with u on the left is equal to, again, we have here e to the negative x times e to the c, right, by the way that exponents work. And what is e to the c but c itself, because it's just a constant? So u is going to be equal to c e to the negative x. And u was equal to 1 minus e to the y. Maybe I should have done something about that earlier. Nah, Nah. Would have made it worse. Alright, 1 minus e to the y is equal to c e to the negative x. Swap these. This is 1 minus c e to the negative x is equal to e to the y, and then natural log. So this is going to be y equals natural log of 1 minus c e to the negative x. This is going to essentially start becoming a linear function as we get further and further out. It's going to be in the negative direction. Oh, no. E to the negative x. Okay. So as as x gets bigger, we're going to have smaller terms overall. Okay. So natural log, get rid of that. Get rid of that too. 1 minus c e times e. No, that'll be fine. Negative x. Add a slider for c, and then we want to take all this stuff. Right, y equals natural log of that. Okay. As x gets really big, right, c e to the negative x gets really small. No, sorry. E to the negative x starts approaching 1. And then we have 1 minus 1. What am I doing? Okay. Natural log. C is 1. This is 1 minus e to the negative x. Oh, that's going to 0. There we go. Phew. I'm okay, I promise. Right, so it's going to start approaching natural log of 1, which is 0, as x gets really big. So that's why that's going to the x-axis as it gets further and further to the right. Then, as x gets really, really small, towards 0, that's going to get us e to the 0 approximately, which is 1, and then that becomes 1 minus 1 approximately. Okay, as c increases, this should mean that e to the negative x has to start approaching as x goes to 0, but c is big, then should take shorter time to get to negative infinity. So it's going to make this side steeper. It's going to be like a steep drop off near 0.5-ish. Nope. That's not what I meant. Okay. But that makes sense, yes. So it's going to get further and further pushed back. So you're going to have longer distance between the asymptote at x equals 0 and where we start going off the graph, wherever we are. Right, these are just big values over here. 2.3. Is it just 2.7? It is. Oh, that's brilliant. I like that one. Right? Because if C is equal to E, 2.718281828459045, then we end up getting a C, which is E. Oh no, X is. If X is negative, if X is 2.3. Okay, now I don't understand. What happened? There. Okay. It's possible that it just missed it. Because, like, the number was too big to get on screen or something. I don't know. That's weird. It's really weird. Alright. If anybody has any questions, let me know. Supposed to be there. I just don't know. Okay. Change the x-axis from negative e to positive 2e. That should make this nice and easy to find. Is 2.3 though, not like E where it's 2.7. Okay. Do we have another one here? Well, anyway. If we decrease, okay, that gets us over to the other side, and then over, or negative, on the negative side, this gets us, it's looking almost like an exponential, but then it goes into a linear function, like hyperbolic almost. It's exponential, but yeah, okay. Yes, okay, no, that makes sense. Because as x starts getting bigger, it's essentially taking a log of an exponential. So the 1 minus c stuff on the inside doesn't really matter. We're going to get a log of an exponential, so it's going to turn into a linear function. If we go the other way, though, right, when c is a positive value, this This ends up with 1 minus this thing, so it can't be negative, because you can't take the natural log of a negative number. I'm going to skip that for now, but can't take the log of a negative number, so the only way to make sure that all that stays positive with a large C is if we have big X values with a negative exponent on there. Okay, and then if we go to 0.9, it's just the negative X values that are going to start making this get bigger and bigger going this way. Alright. I'm mostly satisfied with that. Remembering, of course, that this is not actually the this is not actually the solution, I think. In theory, right? Does that natural log stuff make this any better? Probably not, but u is equal to 1 minus e to the y. So natural log 1 minus e to the y. Okay, so y equals, that's not it. No. Natural log 1 minus e to the y is equal to negative x plus c. Nah, it's equivalent. Oh, wait. Lowercase. There you go. Yeah. Oh. Different values, because our c is part of the exponent here. But when it was out front, it was like here to here. It was e to that power. Because it's an exponent. Okay. Okay. I think this might be a good place to stop. I do have to be up at 6:30. It is now 1. Whee! We could talk some more about Phillips' differential equations. It's got some interesting applications and stuff like that. We can talk about Snedden's partial differential equations at various points whenever I actually fancy destroying myself with mathematics. It's been a long time since I've done partial differential equations. At least with any regularity. Yep, thank you, Phobos, you too. Okay, so who do we have on tonight? Educational-wise, we got Rocket Sage is doing geology. Delively is one of our... they are not doing educational now. However, they have a regular show that they run during the day called May Contain Science. So it's going to be typically science education type stuff. And Science is doing... Belint is doing some art tonight. So... Viewer redemption theme. Art pieces engaging the community. Made it to Partner Plus. Alright. Let's do Rocket Sage tonight. So, Sage is doing some, like I said, geology. Gonna be geology education and some news and things like that. So we will head on over there. Hope you all have a good start to your week. I will get online at some point and do some more math type stuff during the week, and we'll go to we'll figure some stuff out with the other math chads, our Twitch math department, and figure out when we're gonna do good job all together. It's probably going to be, I think they said maybe Monday, next Monday, at like 8 or 9 p.m. my time, which is about noon Pacific. So we'll see how that goes. In the meantime, have a good time, have a good week, and I'll see you later. My name is Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.